Hello everyone, my name is Mr. D'Agostino, Common Core Algebra 2 teacher. We are in Unit 5, Sequence and Series. Today we're going to do Lesson 1 on sequences. There are actually 6 lessons in this packet. Alright, so let's start with Lesson 1. In Common Core Algebra 1 you studied sequences, which are ordered lists of numbers. Sequences are extremely important in mathematics, both theoretical and applied. Now, when I asked you for the first term, the second term, the third term, those are going to be our values for n. Okay, so those are integers. You can't have a term that's 1.5, the 1.5 term. You can't have that. You can have 1, 2, 3, 4, 5, 6. All right, so let's take a look at example 1. A sequence is defined by the equation a of n is equal to 2n minus 1. If I'm asking you to find the first 3 terms of the sequence, all you have to do is plug 1 in for n, plug 2 in for n, plug 3. If they give you a formula what represents the sequence, that's golden. That actually is the best case scenario. If they give you an equation, you can find any term. If you want the 100th term, you put 100 in. If you want the millionth term, you could put a million in for n. This, they're just asking us for the first 3. So that's pretty easy. If I put 1 in, look what we get. We get 1. If I plug 2 in, look what we get. We get 3. If I plug 3 in, look what we get. We get 5. So just by plugging 1 in, you get 1. Just by plugging, so this is the first term, the second term, the third term. If I wanted the 80th term, you'd put 80 in. Now, what I was telling you before is that it's a pattern. Okay, it shows you patterns. Sequences shows you patterns. Look what's happening here. 1, 3, 5. You actually even know the next term without even doing any work. 1, 3, 5, 7. 7, 9, 11. Right? It's going by what? What is it going by? It's going by 2's. Now, what I was telling you before, if you have the equation, you pretty much know what it's going by. This is called an arithmetic sequence. It's going by 2's. Now, it's not a coincidence that there's a 2 next to the n. Keep that in the back of your mind. Which term has a value of 53? Now, if you keep on going with the pattern, 1, 3, 5, 7, 9, 11, if you keep on writing out all the numbers, eventually you'll get to 53. Now, what you would do is you just count how many terms it took to get to 53, and that would be the term of the sequence. Now, that sounds like it's long and drawn out. You probably don't really want to do that. Easiest thing to do is that you just take 53 and you set it equal to 2n minus 1. You solve. Bring the 1 over, right? Divide by 2, and you get 27. So that represents, that's the 27, represents the 27th term of the sequence. So 53 is the 27th term of the sequence. So if you're adding all the terms to get up to 53, you'll notice that there's 27 terms. Now, if you notice 1, 3, 5, 53, 11, 9, those are all what type of numbers? They're all odd integers. So it turned positive odd integers. So it turns out this sequence only generates positive odd integers. So can 70 be part of the sequence? And that is a no. All right, so even if you try to get up all the way up to in the 70 range, in the 70s, you'll actually jump over 70. It'll be 69, 71, 73. Now, if you want to just test it out, what you can do is just like we did with 53, set it equal to 2n minus 1, solve, divide by 2, and you get 35.5. Now, what I was telling you before, n cannot be a decimal. It can only be integers. 1, 2, 3 consecutive integers. 1, 2, 3, 4, 5. Can't be a half. Okay, you can't have a half of a term. Recall that sequences from Algebra 1 can also be described by using recursive definitions. Okay, so when a sequence is defined recursively, terms are founded by operations on previous terms. So if you want the next term of the sequence with recursive definition, you need the previous term. So if I have the first term of the sequence and I want the second term, I have to use the first term of the sequence in order to get your answer. If I wanted the 80th term of the sequence, I need the 79th term of the sequence. I need the previous term. So what this is asking us, let's generate a sequence is defined by a recursive formula. There's your formula. They have to give you the first term of the sequence. Here's your First term of the sequence. I'm going to be using this little tablet that I found in the book room, so just bear with me. I'm going to be using it, occasionally. So let's see if this works here. Now, another thing, in order for this to work out great, these videos should be on the shorter end. So let's see if we can get through these rather quickly. We're really less down. We don't really want a lot of downtime here. All right, so f of 1 is equal to -2. That's the first term of the sequence. Okay, they have to give you a term of the sequence. So now what this is telling you, if I want the second term of the sequence, take the previous term, add 5 to it. So let's see what I have written here. So if I want the second term of the sequence, okay, that's the first term. If I want the second term, I take -2, add 5 to it, because that's what it's telling us to do. Take the previous term, add 5 to it, and we get 3. Now if I want the third term, what do? Take the second term, add 5 to it. Gives you 8. If I want the fourth term, what do? Take the third term, add 5 to it, and get 13. If I want the fifth term, what do? Take the fourth term, which is 13, add 5 to it, gives you 18. So those are the first 5 terms of the sequence. Now again, you see a pattern. What is it going by? -2, 5. Sorry, -2, 3, 8, 13, 18. What is it going by? You guessed it, 5. Determine the value of f of 20. Now again, what I was telling you before with 53, if I want the 20th term of the sequence, I can just keep on adding 5 because we figured out what the pattern is. -2, 3, 8, 13, 18. And you keep on going. Add 5 again. 23. Add 5 again. 28. You keep on going until you get the 20th term of the sequence. Now say you wanted to do this quick. Okay? If I want to do this quick, let's think about what we did to get to the 5th term of the sequence. How many times did we add 5 to get to the 5th term of the sequence? We added 5 4 times. And then we got 20, and then you added -2, and it gives you 18. So that's a quick way to do that. You figure out how many times it's going to take to get to the term that you want, how many times you're going to add the common difference to the term that you want, and then you add the initial value to it. Now it turns out it's always going to be 1 less than the amount of terms you want. So if I want to go to 20, I'm going to add 5 19 times. So let's see if this works out. Let's see if our idea works out. Here we added 5 4 times, and then we added the initial value of -2, and that gives us 18. So that worked out pretty good. So let's see if we wanted to do that with the f of 20. Let's see what it would look like. We're going to add 5 how many times? If it's 1 less than the term that we want. So we're going to add 5 19 times, and then you add the initial value. So what's 19 times 5? Right? That's 95, and then add -2, and that gives you 93. So 19 times 5 is 95, add -2, and that gives us 93. All right, so what you do is just think of that and keep that in the back of your mind, because we're going to be working with that with the next lesson. You want to add, okay, the common difference, 1 less than the term that you want. And then you take that value and add it to -2. So in this case, 19 times 5 is 95, add -2 gives you 93. All right, number 3, determine a recursive definition in terms of f of n for the sequence shown below. Be sure to include a starting value. You need the first term, okay, and they want us to use f of n. So the first term, f of 1, is going to be 5. So f of 1 is 5. Now what do you do to get to the next number? Now you can't add 5. I mean, you could add 5 to get to 10, but what happens when you go from 10 to 20? It's got to be the same number throughout. So it's not adding 5. It's actually multiplying by 2 to get to the next number. So 5 times 2 is 10. Now again, I was telling you before, when you watch the videos, make sure if you want to try to answer the question before I go over it, make sure you pause it. So 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. So you have to multiply. Take the previous term and multiply by what it's being multiplied by. Now that's called the common ratio. Arithmetic sequence, it goes by a certain number. That's called the common difference. In a sequence where it's being multiplied by a certain number, that's called the common ratio. All right, so f of n minus 1 means the previous term. You're going to take the previous term and you're going to multiply it by the common ratio. It's going by 2s, being multiplied by 2s. All right, so let's see if this works. If I want the first term of the sequence, and I have to give it to you. If I want the second term of the sequence, you put the previous term, which is 5, times 2, which gives you 10. If I want the third term of the sequence, you take 10, you put it in, you get 20. So that works out. For a recursively defined sequence, and now we're going to take the previous term, we're going to square it and add 2. That's what this is saying. Whenever you see n minus 1, now they're using different letters. You can use different letters, but as long as you see n minus 1, you have to take the previous term. Now the thing is, we want the fourth term of the sequence. Okay, they only give us the first term, so we have to go through the process here. If I want the fourth term of the sequence, I need the third term of the sequence. So here's the first term of the sequence, which is 2. Now it's telling us to take the previous term. If I want the second term of the sequence, you take 2, you put it in, you square it, add 2. That's what it's telling you to take the previous term, square it, and add 2. And that gives us 4 plus 2 is 6. Now if I want the third term of the sequence, what do? You pick the previous term, which is 6, square it, add 2. To repeat the process. 36 plus 2 is 38. Now if I want the fourth term of the sequence, you take the previous term, which is 38, repeat the process, square it, and add 2. So 38 squared is 1444. Add 2, you get 1446. That's choice 4. All right, one of the most well-known sequences is the Fibonacci sequence. Basically, what that tells us is take the previous 2 terms, add them to get the next term. So they have to give us the first 2 terms of the sequence. So this is what it is, right? The first 2 terms of the sequence is 1 and 2, right? This is this previous term and this is the second previous term, and you just add them. So if I want the third term of the sequence, just add these and gives you 2. All right, so I'm just going to show you what I did here. Here are the first 2 terms. If I want the third term, you just add these 2 together, you get 2. Now if I want the fourth term, I need to add 2 and 1, which is 3. If I want the fifth term, you add 3 and 2, which is 5. And if you want the sixth term, you add 5 and 3, which gives you 8. So take the 2 previous terms and add them. Definitely one of the most famous sequences. It's used pretty much in a lot of different cases. Here is tiling with squares whose sides lengths are successive Fibonacci numbers in the sequence. It actually it's pleasing to the eye. It's pretty cool. One story that I don't think I really told too many people is when I got married, I told my wife, we have twin boys. Okay, I don't care if we have a girl, boy, a twin girl, boy. It didn't matter to me. You can name our children. I didn't care. But if we had twin boys, I was naming them. She agreed to it. Okay, she probably thought we weren't going to get twins or ever have twins, which that was the case. But she agreed. She gambled, and I said I'm going to name twin boys because I have an idea for an experiment on them, but it never happened. If you want to ask me about that, ask me about that. But what my ideas were. But their names would have been Fibonacci and Archimedes. Okay, Fibonacci D'Agostino and Archimedes D'Agostino. All right, so that's what their names would have been. But anyway, it didn't happen. I have an 8-year-old daughter named Ava, and I have a 2-year-old crazy son named Ryan, who gets into everything. But we're working on that. All right, let's move on. Exercise 6. Find an algebraic formula A of n similar to exercise 1 for each of the following sequence. Recall that the domain that you map from will be the set of 1, 2, 3. So What this is telling us, this is the sequence. The first term of the sequence is 4, the second is 5, the third is 6, and the fourth is 7. So if you plug 1 into this formula, you get 4. If you plug 2, you get 5. You plug 6, you plug 3, you get 6. You plug 4, you get 7. So you're going to start out with a of n is equal to something. Now, what is it going by? As you can tell, it's going by what? What number is it going by? 4, 5, 6. It's going by 1, right? Now, remember the exercise 1? It was 2n minus 1. That number next to n was what it was going by. That's a little hint. So if this is going by 1, you should start out with 1n. Now let's see if we can figure out what the other part of the equation is going to be, or formula. If I plug a 1 in, I want a 4. So 1 times 1 is 1, plus what will give you 4? What should the rest of the formula be? Now if I plug a 2 in, I need a 5. 1 times 2 is 2, plus what gives you 5? You guessed it, 3. So there is your algebraic formula. Now let's take a look at the second one. Now this is not an arithmetic sequence. The sequence in A is called an arithmetic sequence. This is a geometric sequence. It's actually being multiplied by a certain number. So this formula is not going to be good. So now, I didn't mention this, but an arithmetic sequence is in the form of a linear equation. A geometric sequence is in the form of an exponential equation. Now, again, we start out with a of n is equal to something. If we take a number and we multiply it by something, it's got to be multiplied by the same number. So say I wanted to take a number like 2, and I wanted to multiply it, say, 4 times. What's another way of writing 2 times 2 times 2 times 2? 2 to the 4th, right? So that's what you have to think about with these type of sequences. It's going to be 2 to the something will give us, hopefully it'll give us 2, but if it doesn't, then you have to multiply that by something. You first have to figure out what your common difference is, okay, with an arithmetic sequence, which was 1. With a geometric sequence, you have to find out what it's being multiplied by. So what is it being multiplied by to get to the next number? 2. That's what your base is. Exponential functions have bases, so does sequences, if it's a geometric sequence. So your base is 2. Now it turns out this works out perfectly. In the next lesson, it's not going to be this nice and easy. We have to work it a little bit. We're going to do that in the next lesson. But this actually works out pretty good. 2 to the first gives you 2. If I want to put 2 in, I need a 4. 2 to the second gives you 4. If I put a 3 in, you get 8. If you put a 4 in, you get 16. So this is the general formula. Now this one's neither an arithmetic sequence or a geometric sequence. So if you notice, again, we're going to start with the a of n is equal to something. See how the 5s are constant on top? We're just going to leave it on top. It's going to be 5 over something. Now the 5 is really 5 over 1. Which is the first term of the sequence. 5 over 2, that's the second term of the sequence. You see a pattern here? 5 over 3, 5 over 4. So what are we going to put on the bottom? So 5 we're going to leave on top. What are we going to put on the bottom? N. And that would generate the sequence. Now, if you have the formula, it's like I said, it's beautiful to have the formula because you can generate whichever term of the sequence you want, the millionth, the thousand. Sometimes you have to generate the formula to get that, which we just did. Sometimes it's not as easy as these first 3, but if you get it, it's like you mastered something. Let's take a look at these last 3 in this question. Now, looks like it's being multiplied by something. If it's being multiplied by something, it's going to be a base raised to an exponent. It's going to be an exponential. It looks like it's going to be like an exponential equation, geometric sequence. So what is it being multiplied by? It's being multiplied by -1. So that's going to be in the parentheses. And again, it works out nice where if you just raise it to the n and you put 1 in, you get -1. If you put 2 in, you get -1 times -1, which is 1. You put 3 in, you get -1 times -1 times -1, which is -1. So that works out nice. Now again, you can do these problems when you're watching these videos. You could pause and try to do these problems on your own. and try to figure out what it is before you get the answer. Now this is going by the same number throughout. What is it going by? It's going by 5s, right? So now, just like I told you before, that's an arithmetic sequence. So it's going to be in the form of an equals 5n, because that number that it's going by, that's going to be the number in front of the n. Now we have to figure out 5 times what? Sorry, 5 times 1 plus what will give you 10, because that's the first term of the sequence. If I want the second term of the sequence, 5 times 2, which is 10, plus what will give you 15. So what's the other part of the equation or the formula? You guessed it, 5. Now f is like the previous in the previous question, previous part of the question. This one, see how there's a constant on top, constant of 1. So you know it's going to be an equals 1 on top. Now what's going to be on the bottom? What do you notice about the numbers on the bottom? They are perfect squares. How do you get a perfect square? Take any number and you square it. You're right. There it is. If you put 1 in, you get 1 over 1 squared, which is 1. 1 over 1 is 1. If you put a 2 in, 1 over 2 squared is 4. Or 1 over 2 squared, you have 4 on the bottom, so that's 1/4. So that works out. All right, last question. Which of the following would represent the graph of the sequence? Hopefully we're doing good on time, because I want these lessons to be shorter than they've been, because it works out better that way. Try to get as much information in the video as possible with the short amount of time on the videos. All right, so here's the formula. Look at that. They give us the formula. If they give us the formula, we can generate as many terms of the sequence we want. It's like it's great to have the formula. So let's do that. Let's put 1 in. What do you get? 3. If you put 2 in, you get 5. You put 3. Now you know what the pattern is. 3, 5, 7, right? 9, 11. Now which of the following would represent the graph? All right, so there's 1, 2, 3. Now we don't start at 0. We're not starting at 0, so it can't be 1. And we don't connect the dots with a sequence. So we just use process of elimination. The answer is choice 3. And it makes sense. You go over 1, up 3. Go over 2, up 5. Go over 3, up 7. There it is. It's choice 3. I hope you liked the first lesson. What we're going to do tomorrow in class, or the next day in class, you're going to get into groups and you can do the homework. Okay, so hopefully you enjoyed the lesson, and look forward to more positive and fun lessons. Enjoy the rest of the day.